Welcome back. And now we're gonna finish our session of classes about how residual turn into free phase and vice versa. We'll have some bonus lectures for you if you think a lecture could be a bonus, but that's okay. If you're paying for the course, it should be a bonus, okay? And you have to take a close look. We have a very enough beautiful, well, I can't describe how interesting is the gasoline spill that was actually filmed by Juliana Freitas, a former student by Jim Barker and of mine as well. So this is very good movie, and you have to learn. You're gonna see an actual spill happening on a section of a glass porous media. It's just amazing. For you who likes this subject, you'll be really amazed. So this bonus lectures will be available for you, and you do have to take a close look. Well, now back again to our talking. Well, we have seen that during imbibition, as the wetting phase in our situation there, water displaces the non-wetting phase, free phase might become trapped due to snap off in the situation of the pore and turn into residual phase. Well, that is understandable. We've seen that. Well, the question then is, and what does happen during drainage? How does residual phase switch back to free phase again? Well, 3 fluids is the answer. Well, I'm going to show you that. But before I show you that, you have to think about one situation. I showed you and told you already, when you're talking about this displacement, it's always about one fluid pushing the other and vice versa, right? Well, when you're talking about residual phase, can you imagine a situation where you have the top of the water here and you have residual phase here underneath the water table? No free phase. Forget about free phase. All we have is some residuals trapped here. As our water is moving downwards, the water table is moving downwards. You see the water table moving downwards here, right? It is moving downwards. Well, what do I have here? What do I have here? I have air. I have air, right? It's the water table. And I have water here with a few residuals in between. As this water table is moving downwards, you have a contact between air and water. Air is the non-wetting fluid now, and water is the wetting fluid. But at a given point, what we'll have is the air touching the water and the residuals. And we will have some situations and something happening just because we have that. Well, take a look at this situation here. We have air, we have water, and we have oil. That's a situation of a typical spill of oil on the ocean. Well, think about a situation when your oil is on top of a very smooth surface. No waves of any kind. It's very completely smooth. Well, this oil will tend to spread laterally, indefinitely, until it reaches a thickness of 1 molecule. Really, that's how Avogadro's calculated this number, by spreading a non-wetting fluid on top of water and measuring the area, and then estimating the amount of molecules there was in. Okay, so it'll tend to spread indefinitely, right? Laterally. That's exactly what happens in this situation here. We just don't have a porous medium. Well, should we have a porous medium here, like we would have here a grain and here another grain, okay? what would happen is that at a given point you would have water, air. When this guy goes down, water, air, and oil touching each other. You have three fluids. Three fluids. Instead of two, we've been dealing with two fluids and a surface. Now we have three fluids and a surface. And what happens is that the fluid that has an intermediate density tends to spread on top of the fluid of a higher density. Well, if you have a residual phase here, right? You have a residual phase here. This residual phase, as it touches as it's being touched by air, tends to spread on top of the water. But this water actually is distributed among the pores, and it then moves laterally again. Well, as it moves laterally, it becomes mobile again. And this remobilization of the residual phase is due to the presence of a third fluid, a less dense fluid, in our case, air. And that's why the residual phase becomes free phase again. Okay? Well, let's take a look at this situation here. Well, now you have everything that I said is written here for you to use, and it's going to be distributed on your handouts. Well, take a look at that situation here. We've seen this before. We have our water table here, and you have a bit of a capillary fringe. And then we have one spill. You can say that this is an El-Nepo easily. You're good students, you know that. Well, I put wells here. Another well here. First, look only at this well here before we look at the other. We have, as you may realize, you have the water level inside the well corresponds to the level of the water table here. And outside the well, the water is on the capillary fringe here. The well is so big, has no capillarity, so all we have here is atmospheric pressure. In this case here, take a look. Shouldn't we have this El-Nepo here? We would have the same situation. Well, but what happens is that we do have the El-Nepo here. And the El-Nepo then invades the well. It does invade the well. If it invades the well, it comes inside here. Well, but look at this interesting thing. Instead of acting like this one here, you see, you had the water table here. It pushed the contact down here. Water is down here now instead of here. And why that happens? Well, I'll give you the explanation. You see that our fluid here is above the water table, and it moves inside the well because it is a non-wetting fluid, and non-wetting fluid likes larger pores, and the well is a very large pore indeed. And it moves inside the well, and as it moves inside the well, and you have water on the other side, you have to think of this column of water here. This column of water plus this bit of El-Nepo. But if you think of this column of water here, that's what would happen should you had no El-Nepo here. The column of water would be this big. You can compare this well here, the same, and here we have this guy. Well, what we have is that the column of fluid here, a less dense fluid, has to push the water down to equilibrate the pressure. Okay? That's what happens. Well, this is called apparent thickness, and we're going to talk about this. And this is called real thickness. We have this much product in a porous media, and within the well we measure this much product. Okay? Well, this situation is very interesting. Take a look on our YouTube experiment here. Look, should we have only water here? They equilibrate at the same elevation. Well, but then we put oil here, and you see that this column of oil now has to equilibrate with this column of water. So the pressure at the same elevation here of water, here we have the contact, so we have water, has to be the same. So the pressure of oil, of this column of water at this elevation, and the pressure of water is the same. I use A here because water in Portuguese is água, and I use that in my videos in Portuguese. So sorry for English speaking people, you have to think that as a W. Oil, água. Okay? Oil, water. Well, now we have the height of oil, height of água. Height of oil, height of água, or water. And then, at equilibrium, we have the pressures, and we can equal the pressures. Density of oil times gravity times height of oil. Density of água times gravity times height of água. And we can actually calculate the difference. When you go to the field, what you measure within the well is this here, air, oil, this interface, and then you measure this other interface, oil, água, or oil, water. And then you can calculate back the water elevation, and you can correct for the position of the water table at that point. And with that explanation, we get to the end of our lectures. You please take a good look at our bonus lectures, and we will still have some good questions and some good explainings of the real field situations in our tutorial. Thank you very much.